Well, it's okay. It's already the last talk of this season, but I hope that we will all then reconvene in October for the next season, which will already be the 14th season so far. I'm very happy that Professor Daniel or Dan Le Heron will be our speaker today. Daniel is from the UK. He studied in Wales and also did his PhD there. He had a number of postdoc positions afterwards, for example, in Strasbourg, Hanover, and Cambridge, before he joined the Royal Holloway University in London as a lecturer. After about 10 years in London, he finally moved to Vienna about 8 years ago, I think, as a full professor for sedimentology. And Daniel's expertise and passion are glacial systems. I would say any type of processes related to ice sheet and glacial dynamics, erosion, sediment transport, also sediment deformation. His research covers all geological time spans. Amongst others, he used sedimentological evidence to reconstruct past glaciations in the Precambrian and also in Ordovician times. And now, being based in Vienna, you can already see his first slide here. He also works in the Alps, aiming to understand glacial processes, but also kind of whoa. Also, sorry, working on the sediment budgets related to the recent deglaciations. Today, Daniel will talk about the, as you can see, glacial lineations. And so, Daniel, I'm happy to hand over to you.
Lovely. Thanks very much, Michaela, and thank you for the warm introduction and for the invitation to talk today. I hope that what I present will be interesting, hopefully deep enough for people, but also for the non-specialist in sedimentology, you'll have an idea of what we're talking about. Okay, so there's going to be a lot of photographs in this presentation. I'll leave you with this impression to begin with, because what you can see is a landscape in the Ötztal Alps in Austria, which is in Tyrol. And what you're looking at is an area that was deglaciated in the last few decades. And what you can see maybe on the screen is you can see that there are some meltwater channels which are coming from the glacier. You can also see that the whole area is covered by sediment, which is good for a sedimentology lunch. And on the surface, there are some boulders that are dotted around. And in front of those boulders, there are these elongate features called glacial lineations. So we're going to look in these in some detail and think about how they form and so on. Okay, so the main focus will be on what we can extract from the ancient record, because this might be a surprise to you or to many of you here, but what we look at in the ancient record is often better preserved and contains more detail than what we can see on the present day surface of the Earth, which I hope is a surprise for people. Okay, before I begin, yes, my name's Dan. I'm here in the University of Vienna, and what I'm going to show you is basically the majority of this presentation is from a manuscript that's in review at the moment. Okay, and because it's in review and it's not just me, there's a whole series of other people involved in this work. So I have a wonderful team here in Vienna. Ricarda and Pauline are finishing off their PhDs, modern and ancient glacial stuff, and Siegfried will be starting soon. And I've got colleagues in the University of Johannesburg, Berta Smit, for example. I have Saeed Tafai from Saudi Aramco, who's made an important input into this story too. We've got friends from France, from the CNRS, in particular Pierre Dietrich and Jean-François Guienne in this particular piece of work. Although I see also Laurent Gendre there online. Hello, Laurent. The team from Aberystwyth University, Marie Busfield and Sharman Jones. Okay, so it's a collective effort here. Right, so let's strip it all back. We can go to this wonderful outcrop here in South Africa. It's 300 million years old, and it's only appeared because the river has receded at a low level when we were there and exposed this wonderful surface. There are these linear features, but the question is, how do they form? And how do we know that they form in a particular way? Do they tell us anything about the conditions at the base of a glacier? Do they tell us anything about how rapidly the glacier flows, and so on and so forth? So all of these questions are in the background as we look at these images, okay? Firstly, you'll see a person here. This is Marie Busfield standing on the outcrop. And you'll think, well, great, how can we demonstrate that a glacier was there anyway? These things could be formed through a big underwater landslide or maybe some other process that we haven't yet thought about. But the good news is we've seen them in the Alps and we can see them forming under modern day glaciers. So this might be a bit slow as it rotates, but don't worry. You're looking at the Gepatsch fauna here, the Gepatsch Glacier in Tyrol from a few years ago. And this series of linear features is emerging from underneath it as the glacier is retreating. And you can see these things here, which we call flutes, being generated. So we know they form under the glacier, and we know that if we look at ancient examples, they're expected to form in the same way. That's the first important point for the talk. Okay, what else we can see on this slide, which I'm not going to talk about today, is, sorry, I've gone ahead of myself, is hard bedrock. And the bedrock here is shown in a yellowish brown color. You can get all sorts of linear features, glacial striations forming on bedrock, but we're interested in what happens in the sediment when glaciers are sitting on sediment and shearing it and forming these lineations. And Paulina has been doing a wonderful job of mapping the Fanacht fauna forefield. This is the same area I had in my first shot, this oblique view from the drone, and exquisite detail with regards to mapping these glacial lineations. And we can see what happens to them as they form from one year to the next over time. And we can measure their lengths, we can measure their widths, and we can start to think about them as maybe separate features, or maybe ask whether all of these lines that you see are related somehow in one continual process. Okay, so just to point out a couple of things, on the right hand side on the interpretation here, we've got flutes that are marked. These are these features that form behind boulders. Okay, I'll explain to you in a minute how they form, or how they're thought to form, as a basis for the rest of the talk. You can also see that there are larger linear features here in orange, which are referred to in the legend as streamlined features. There's no particular word attached to them, but just streamlined features. If we look at an interpretation of that, a field view, there are flutes, streamlined features that we are calling, using the word streamlined features. Sometimes we see other words in the literature, and we're probably not going to remember all of these terms, and they're not that important to the presentation. We also see that there is other stuff going on. There's stripes of debris that form on the glacier, and as the glacier melts away, that debris is let down onto the surface of the forefield. So when you're looking at these features, these forefields as a whole, they can be quite complicated, which is why Paulina has been mapping them in such detail. We can look at these forefields in more detail. There we have our lovely boulder, and lo and behold, just behind it, we have a flute. In each of my pictures, I've got an arrow, and the arrow indicates the direction of ice movement. So in this case, the ice was moving from the top left of the picture to the bottom right, and you can see the scale bar down here to give you an idea of how big these things are. Usually 20 to 30 centimeters, maybe 50 centimeters wide, up to tens of meters long. On the ground, they're not as easy to see. If you're walking around doing conventional field work without a drone, then you can see these structures quite clearly, but they're not so well developed as when you have the uncrewed aerial vehicles at your disposal, where you can look at digital elevation models and do clever things with lighting. So that's important. What we see also is that all of this material is unsorted. We see a diamict. That means a unsorted sediment, big boulders, there's clay in there. There doesn't seem to be any systematic organization to the deposits. Okay, that's an important observation from these modern forefields. Now, on to how these flutes actually form. Remember I said that there's often a boulder up ice and the flute develops down ice of the boulder? Well, there's a lot of debate about precisely how this works. But one popular and, dare I say, well-accepted interpretation is this one by Ives and Iverson in Geology 2019. And they basically did a lot of isotropy of magnetic susceptibility work on the sediments in Iceland on one particular flute, and were able to figure out in which direction the sediment was flowing as the flute was forming and shearing was taking place beneath the glacier. So the general idea is that you have a boulder here in picture A, and behind it there's a cavity. So the sediment will flow up into the cavity. There's also water in the cavity, and over time, a bit like in the pressure shadow in a metamorphic rock, you would have, for example, in a deforming rock, a garnet, you have a pressure shadow, and minerals tend to accumulate behind that. And so this is the same process happening in a flute. And over time, what happens is that the water gets squashed out and the till, this unsorted material, gets compacted. And as it gets compacted, it's then becoming so strong, so hard, it's doing the job of the boulder now. Okay, it's causing another cavity to propagate behind it, into which more sediment flows and the flute can become elongated, in theory, up to an infinite length. That's the general idea, just to understand how these things actually develop and get so long. Okay. Another question entirely, and this paper was only published 2 weeks ago, or maybe just last week, but I felt desperate to try to include it to show it because it's a really good paper. The things we've seen are quite small, but you can perhaps scale them up. At the size of a landscape, you can see big lineations, mega scale glacial lineations, they're known as here, MSGLs. And perhaps these things form part of a continuum of structures, a bit like the different lineations you would have on a fault surface. Okay, there's a hot debate going on about that. I just want to introduce this as a topic and we'll return to it. That's the basis of the presentation. That's where I wanted to begin with. Now we're going to get into it. Okay, and I want to use the Paleozoic as a shining light on these processes because the quality of the outcrops are exceptional. And there's a reason why they're exceptional. And I'll dip into this reason as I go from one slide to the other. Okay. If you look at this slide, hopefully you see immediately that these are the same structures that we were looking at before. There's a boulder, there's a flute, and one thing I have forgotten is a scale bar, but the scale is approximately the same, okay? A few meters, or perhaps 10 meters long and 50 centimeters wide. I've used the word Paleozoic as a general word because I want to draw on late Ordovician and end Carboniferous examples. Okay, so that means that I can put Africa and South America together on a map like this and show where our study areas are. And some of them were produced during the glaciation of Gondwana during the late Ordovician, and others were produced during at a later stage during the late Paleozoic. Late Ordovician examples about 443 million years old. The late Paleozoic examples about 300 million years old. And that's pretty well constrained for the sections we're looking at today. Okay, so I'll go through some of these and show you the highlights, and hopefully we can get a flavour of what's familiar, what's different, what's a bit awkward and uncomfortable when we're trying to make our interpretations. I'll start off with a place called Pacus in South Africa. And this is a late Ordovician example. And I've shown you a map. The map has on the left-hand side a drone image, an orthomosaic made from lots of different photos stitched together in a standard way now and interpreted in Aggie soft meta shape, the completely standard workflow in sedimentology. And on the right-hand side, I've had a go at interpreting it. And what I wanted to show you was that we have these wonderful flutes that you can see. We've got also lots of smaller scale structures. I'm afraid the rest of the legend has gone off the screen, but we have striations as well. And the thing that makes this unusual now is that we are talking about striations in soft sediment. And that is something that is very, very rare in the modern record. Let's look at the view of these rocks on the ground in a minute. But before I do that, I wanted to just point out, before I forget, we've got two units here, the Steenbras member in yellow and the Kobe member in pink. And the Kobe member is sitting on top of the Steenbras member that contains all of these wonderful structures. Okay, so I'll focus on this relationship as my first point in the next slide. Please look at the bottom right-hand picture. You can see this relationship clearly. Okay, the Kobe member here is a marine shale, and it contains trace fossils. It contains an invertebrate fauna that are of a marine character. This is the unifying aspect to this set of outcrops. They are all overlain by marine deposits, and we assume that these glaciations were taking place in a marine setting. That means that the glaciers reached the sea, and these whole features that you can see, these flutes in the top left-hand picture, close up here on the top right, and these soft sediment striations are all forming in a marine environment. Now, the first thing that you might think is, what are you talking about with soft sediment striation? Well, I've got a hand specimen here for you to show you. This is a sandstone. My wife said to me when she learned about sedimentology lunch, she asked me if I was going to have sandwiches for my lunch. I didn't laugh at that joke. But this is entirely made of sandstone. Okay, that's unusual. If you look at modern glacial deposits, they're mostly made up of this unsorted material. In the Ordovician, almost exclusively sandstone. That's the first thing that makes it a slightly unusual glaciation. The second is, if you look at my picture in the bottom left-hand corner, you see that these soft sediment striations are stacked one on top of the other. That's unusual. Does it mean that the glacier has been back and forward many times over the surface, or did they form during one process of shear? If you can imagine, if you go to the beach and you run your hands through the sand, you can create a series of grooves and ridges, just like this. And so we think that these form in a similar way, with pebbles perhaps grinding away on the surface of the sand. That's enough of an introduction. There are enough characteristics here for us to recognize when we shift continents now, or shift subcontinents and move to Arabia. And in Saudi Arabia, we see a very similar assemblage of structures with a few differences, a few extra things to add to our palette here. We see evidence for meltwater channels that are cross-cutting these surfaces. We see these interesting plough marks. Again, the blue arrow is always indicating the direction in which the ice is flowing. Okay, and in the bottom right-hand corner, we have a different impression left behind. Okay, if I go back to the previous slide and you look at the bottom left-hand corner, you've got one bed of sandstone overlain by the other, and they both have these striations on the surface. In the one here in Saudi Arabia, by contrast, they form these lobe-type features. So I'm going to use this term lineated lobe because I think it does the job. It may not be perfect, but you can see that it's a lobe-shaped feature and that there are lineations on the surface. And what I want to show is that these features are recurrent in a number of different settings at a number of different scales. Okay. You have beneath these surfaces lots of evidence for internal deformation. So we know that some degree of shearing of the substrate beneath the glacier was taking place. That's not a problem. We understand that to some degree. What I have my arrow pointing on here in the left-hand picture is one of these soft sediment striated surfaces poking out of the stratigraphy, just to really show you that they are developing within the sediment column. Okay, we can move around to another part of Saudi Arabia, Al Aib. I'm sorry, this is on its side because I wanted to expand the pictures to make them as big as possible. And when we look at satellite images here, we can see a lot of linear features. And I thought to myself, this could be literally anything in geology. It could be faults, it could be fracture networks, it could be perhaps even aeolian structures, linear dunes in the desert. So you have to go and check the outcrop and see what's there. And the rest of the slide shows what's there. And we can see at a smaller scale, we have flutes. We have Said here sitting very excitedly on a sandstone that is overlying the surface with glacial structures on it. That's a marine sandstone. And the surface of the sandstone is deformed by lots of different grain flows that cross-cut the surface. We're going to switch back now to South Africa because I want to talk about the late Paleozoic, just seamlessly from Ordovician to late Paleozoic to see where the connections lie. And we've seen picture A already. This is what some of the rocks look like on the ground in picture B on the right-hand side, top right. You can see these boulders lying around. There's one I'm highlighting now that is just at the up glacier end of the flute. But now it gets really exciting when you've got the drone's perspective, because in picture C, you can see that these features, the flutes as we call them, they actually form at multiple levels in the stratigraphy, just like the soft sediment striations do, in a very similar way with similar kind of geometries, set 1, set 2, and an upper set, all one on top of the other in this layer of rocks. This is a very much an overview here. Ricardo Wollschlegel has an extremely detailed high impact paper that is hopefully going to come out soon in Gondwana research. Still being a bit patient on that, but again, to emphasize that I'm pulling together ideas here, but they are doing the absolute groundwork and the amazing detailed science on the ground. There's Ricarda in the bottom right-hand corner, and she's standing on this surface with glacial features, and just to the left of it, again, the unifying factor is we have an onlapping shale, a marine deposit. And so largely this is a preservational story. We're getting insight into what's going on in a glacial marine environment, and that preservation from fine shale deposition mixed in with the deposits on the seafloor is leading to exceptional preservation. And that's why the features that we see are much clearer with much more detail than we see in the Alps in a modern terrestrial environment. But it's also really worth pointing out that this is very valuable in understanding what's going on beneath the modern Antarctic ice sheet, because we often rely on things like isolated cores to get an idea of the sedimentology, or else we're looking at different geophysical techniques, and the resolution is lower than what we are able to achieve here. So the Paleozoic record has a lot to bring to understand what's going on beneath modern retreating ice margins in a marine environment. And the preservation story continues and continues. The more I look at this, the more there is. I really want to be there. If I wasn't giving this talk, this would be the next thing I'd want to do. To give you a perspective of these lineated lobes, see the same term but scaled up now, with flutes superimposed at different levels. They also scale down a bit. We find flutes that are a little bit smaller there. And on the bottom right, we've even got striations on bedrock overlain by centimeter scale lineated lobes, sediment that's plastered on the surface like that. In the top right-hand picture, we have a similar meltwater channel like we saw in Saudi Arabia from rocks that were 130 million years older, sorry. And final example from the Paleozoic would be Orlog's Kloof in South Africa, another amazing outcrop. We published on this in 2019, did a bit more work on it. I just wanted to bring it back because it's an exciting outcrop and it emphasizes the point that these features are superimposed, stacked one on top of the other with repeated patterns at different scales. Right, I promised you an answer, or you want to have an answer. How do these things really form? Does anybody want to know? I presume so. There are lots of models you could choose if we go into the literature. We have, in the bottom left-hand picture, the model of O'Brien and Blick from 1992. There's the base of a floating ice sheet, and it's touching down on the seafloor and producing these grooves. That's nice. We have another obvious one. Icebergs maybe scouring the seafloor. What we would expect to see in those cases are lots of chaotic patterns when you map them using satellite imagery or aerial photographs. And in most of the examples we've seen, we haven't seen that, with one exception, and that is the Orlog's Kloof example in the last picture. So that's mostly not applicable for most of the rocks I'm showing you today. And then the final example that really got a lot of traction and with different modifications was this idea of shear within the sediment column. Different workers all coming on board with this with slightly different nuances, but the general idea that the ice is moving over the sediment column, the sediment is shearing like a pack of cards, and you get these features forming at different levels. Now, what I would say to that is that they're all very nice models, but in our case, they're probably all wrong, including the last model, including the last PhD chapter that I wrote all those years ago. So the question is, how exactly do they form? I'll continue to answer this question. There've also been discussion about whether these things are all related to each other. Different people have assembled geometrical data, the width and length of different structures, and plotted them on big Excel spreadsheets, and have argued that some of them are forming in a different way, separate to the larger population. What we could do, at least for our data, was to plot all of the lineations for each of the different sites. And there's 316 here that we could measure confidently. And what you can see is that we have got a consistent scaling relationship. There's a nice linear fit that is the solid line here, and the power law fit is a dashed line. And what's interesting is that we can look at the smaller end of the spectrum here. So for Siegfried's future PhD, the hope is to look at the laws of scaling relationships and their interpretations for the smaller end of the spectrum and link it into the larger structures that we've seen in the Fanacht-Ferner glacier region, for example. Okay, so moving on. So I wanted to give you a visual reminder of where we are with things. And I've made the case that, at least to my eye, things can occur at different scales that are at least geometrically identical to one another. We can make that case with the scaling relationships based on the data that we've collected from each of those different examples. But one area that we do not fully understand is the why. And we can look at the modern seafloor of Antarctica, somewhere like the Weddell Sea. And this is in fairly deep water, several hundreds of meters. It's not my work, it's by Jeff Evans and Kelly Hogan in a big Geological Society of London publication from 2016. And this is geophysical imagery of the seafloor. And you can see the scale here. This is 2 kilometers wide. And one on top of the other, we get these lineated lobes. At this scale, we talk about grounding zone wedges. So where the ice is grounding on the seafloor, you may get a little bit of floating, sediment gets deposited, and then it grounds down again. And over time, you get this accumulation of stratigraphies. Set 1 at the bottom, set 2 in the middle, set 3 at the top. And I would argue that this process is repeated down to the centimeter scale that we can see here in Saudi Arabia going back 443 million years. We can see lineated lobes again in sandstone, set 1 overlain by set 2. An intermediate scale example, both in terms of the size of the structures and in terms of the age, comes from the example in South Africa I showed you from Harrisdale Farm that Ricardo has been working on intensively. And once again, one set of lineations overlain by another and topped by a third set on the top, like so. So we started to think about how this all fits together. And what we learned from the process is that at the moment, very little is published on the generation of these lineations when you look at the outcrop scale in a marine glacial environment. And that's simply due to things like accessibility beneath modern ice sheets, the logistics of everything, and of course the resolution constraints that are there as well. So we can start to compare and contrast the assemblages of things that we have on the bottom, the left of the diagram is the kind of situation we've been talking about today. What happens in a marine environment at a tidewater glacier, and how all of these different features fit together. I won't go through them all in detail unless people want more detailed explanation in the questions. I'll just leave that there for some thought. But it's the marine aspect that facilitates, firstly, a greater range of structures that we see, and it is the marine environment that allows that greater range of structures to be preserved via shale that often caps and seals and preserves these structures so wonderfully in the ancient record. So we've got that. If we look at the terrestrial situation that Paulina had for her map that I showed at the beginning of the Fauna, well, the structures are certainly impressive and they're wonderful when you map them, but the range of structures is evidently much reduced. And that has to do with the terrestrial setting, the fact that we have less settling out from in a water column to give you this finer grained material we often see in the ancient record, more sand, more sandstone, more silt, and the chances of things to become rapidly removed very quickly after deposition. So I'd like to give you a few reflections on things. I had hoped to animate this, but obviously I was at the limits of my technological capabilities today. Just 3 points really to take away for us. That we can develop a new conceptual model for how these glacial lineation fields develop in marine glacier margins, and we can anchor that in Paleozoic observations. And I think that's really exciting because we're always asked as geologists, well, why do you look at these old rocks? What relevance do they have for the present day? Well, we can make the case very strongly that we simply don't see that range of structures in the modern record because we can't, for the reasons that I've given you before, and yet they permit insight into what's going on beneath the modern marine glaciers. The second point would be this idea of this scale continuum that is still a topic of hot debate, I think, in glacial geology and sedimentology generally. But we see this continuum over 3 to 4 orders of magnitude within our data, and also scaling things down to the very small scale, which has not been incorporated in any previous work that we're aware of to date. To add to that, not just this linear development, it's also the stratigraphy, the development of lobes, and the recognition that we may have, with question marks and a lot of caveats, scale invariant sediment packages with lineations developed on them. So you've got the combination of sedimentation, probably beneath the glacier, and shear, all playing a part in the development of these rocks. The final thing I'd like to say is many thanks to the various bodies that have funded this work. I've now lost track of how many have helped us along the way, because this is something that has been compiled from many years of work. But I'd like to say in particular, thanks to the International Association of Sedimentologists, the Geological Society of London, to Saudi Aramco for the field work in Saudi Arabia here, and to the University of Vienna from my side personally for the support in making the field work happen. My collaborators have their own funders, and I'm sure that they'd be grateful to those too. Great, so that's it from my side. Thank you very much for listening.